All right, in this lesson, we are going to go more in depth on solving absolute value equations. So here we have a list of steps. Your first step is to always isolate the absolute value bars. Okay, and so get everything outside of the bars away before you start writing your cases. And after you have isolated the absolute value bars, you set the argument of the bars equal to the positive and negative form of the other side. Okay, after you do that, you're going to solve each case. So you're going to have two cases and then check for extraneous solutions. So starting with number one, these absolute value bars are already isolated. There's nothing going on outside the bars. And so we are ready to set the argument equal to the positive and negative. So this is the argument. X minus 6 is the argument. It's the expression inside the bars. And so we set that expression equal to the positive eight. Just color coding this. And then we also set the x minus 6 equal to the negative 8. Setting the argument equal to the positive and negative version of the other side of the equation. So in this case, it's just an 8. Sometimes we'll have another expression. And so here's our two cases to solve. They're two linear equations. In both cases, we have to add 6. So I get x equals 14 as one answer, and x equals negative 2 as the other answer. And so you can write your solution as a set of numbers if you want to, usually listed in numerical order. You don't have to, it's just sometimes they're written that way. And to check for extraneous solutions, you want to plug these values back in for x and make sure they actually work. So if I plug in negative 2 for x, I get absolute value of negative 8, which we know is positive 8. And then if I plug in the 14, I get 14 minus 6, which is 8 inside the bars, and we know the absolute value of 8 is also 8. So always check your answers. Okay, next step. First step is to isolate the bars. Here's the bars, and there is a 5 outside. It's being multiplied. And so in order to get rid of it, we have to divide. That is the inverse operation. And so we divide both sides by that 5, leaving us with n plus 10 inside the bars equals 2. Now that the bars are isolated, we need to set the argument, which is n plus 10, equal to positive 2 for one case, and then n plus 10 equals negative 2. You set the argument without the bars, no more bars, n plus 10 equal to the positive and negative version of the other side. And then from there, you just solve your two linear equations. And so in one case, we get n equals negative 8. In the other side, we get n equals negative 12. And so if we check those back into the original equation, we get, just rewriting the equation here. If I plug in the negative 8, negative 8 plus 10 is 2 inside the bars, times 5 is going to be 5 times 2, which is 10. So that equation, that solution works. And then if I plug in negative 12, negative 12 plus 10 is negative 2 inside the bars, which when we take the absolute value of negative 2, it becomes positive 2, which is 10. So both solutions work. Okay. Number 3, there's nothing outside these bars, and so we are ready to set up our cases. And so we set the argument negative 9x equal to the positive And we set the argument, negative 9x, equal to the negative. The argument is negative 9x, no more bars. And then 63 is the other side of the equation. We have the positive and negative. And so now we just need to divide both sides by negative 9, and we get negative 7 and positive 7. If we plug in negative 7, we get positive 63 inside the bars, which does equal 63. And then same if we plug in positive 7, we would get a negative 63 inside the bars, but after the absolute value, it would become positive. So both of those solutions work. Okay, next, here's the absolute value bars and the argument. So we need to get rid of this 5 first. Because it is being divided by 5, the inverse operation would be multiplying both sides by 5. So that leaves me with just a 3v minus 2 on the left and a 25 on the right. So we are going to set the argument 3v minus 2 equal to 25. And then we have 3v minus 2 equals negative 25. You set the argument 3v minus 2, no bars, equal to the positive 25 and the negative 25. And then we solve by adding 2 and then dividing by 3. So we get v equals 9. And then in this other case, when we add 2, we get negative 23, divide by 3. And if you get a fraction, just simplify your fraction as much as possible. 23 and 3 are both prime, and so that's the best we can do for our solution. And so to plug these back in to check them, I'm going to rewrite the original equation, 3v minus 2 divided by 5, and we need to make sure that equals 5. Okay, so first let's plug in the easy one, 9. From that, I would get 27 minus 2, which is 25 inside the bars. Absolute value of 25 is just 25. Divided by 5 is 5, which works. Next, plugging in the fraction. Negative 23 over 3. Plugging that in, the 3's would cancel, leaving me with just a negative 23 minus 2, which is negative 25 inside the bars, which becomes positive 25. And we still have the division by 5 from the very beginning, this division by 5. And so we get 5 once again. You don't have to erase that work. It's probably best to show it, but for the sake of the notes key, I want to keep it clean. All right, number 5. We need to isolate these bars, and the only thing inside the bars is x. So after that, we'll practically be done once we write our cases. So first step is get rid of the number that is not attached to the bars. So you have to subtract 2 first. Some people think of it as reverse PEMDAS. And then we can divide by the 4. So the bars are still here. And we have absolute value of x equals 7. So now when we write our two cases, our argument is just x. And so in one case, we set the argument equal to 7, positive 7. And then our other case, we set the argument, which is just x, equal to the negative 7. And then we're done. These are our solutions. And you can plug those back in and see that they work. And so negative 7 and 7 are our final answers. Just writing all my solutions in set notation. Again, you don't have to do this. It just may be like that on a multiple choice quiz or test. All right, number 6. When I subtract 2 from both sides to isolate the bars, I get absolute value equals -10. And we know that absolute value is always positive. Anytime you have the bars around something, it never equals a negative number. And so when you have a case where you have absolute value bars equal to a negative, stop. Don't write your cases. Don't keep solving. It's no solution. There's no way absolute value of x could ever equal -10 because absolute value measures distance, and distance is not negative. Okay, now we're going to have some absolute value equal to expressions. And so this is where extraneous solutions can come up. In the case of 1 through 5, where we had an absolute value expression on one side and a positive number on the other, you don't really run into extraneous solutions. It's always good to check your work anyway, like I modeled, but you don't really have to. Whenever you have absolute value equal to a negative, you shouldn't keep solving. Both of your solutions will be extraneous if you find them. And so just stop and say no solution. For number 7 and 8, these are where we have to check for extraneous solutions because we have a variable on both sides. So check for extraneous solutions. Okay. So whenever you have this case, always still isolate the absolute value bars. In number 7, that's already done for us. And then we still set the argument, which is 2x, equal to the positive and negative version of each side. So my argument is 2x. That's going to be consistent. We set it equal to the positive, which copy it down just like it looks, 1/2 x plus 6. And then to set it equal to the negative, we distribute the negative. Every term becomes negative. So -1/2 x minus 6. If there was already a -6, I would have made it positive. You basically flip the sign of everything on the right-hand side. Okay, and so from there, we're back to solving a linear equation. And so I'm going to subtract 1/2 x from both sides. 2 minus 1/2 is 1.5 or 3/2. And then to get rid of a 3/2, we can do it in steps. This is being divided by 2, so we can multiply both sides by 2. To get 3x equals 12. And then we can divide by the 3 to get x equals 4. Okay, over here we are going to add 1/2 x to both sides, which would get us 2.5 or 5/2 x equals -6. To get rid of the 2, we multiply by 2, giving me 5x equals -12. And then we can divide by the 5, giving me x equals -12/5. Okay, and we have to check both of these for extraneous solutions. So we'll start with the easy one, the 4. And when you're checking for extraneous solutions, always go back to the original equation before you started doing anything. Okay, and so absolute value of 2x equals 1/2 x plus 6. So setting up the equation with bars and replacing the x's with parentheses, because we're going to use that for both. Okay, in one case we are plugging in the 4. In the other case, we are plugging in the -12/5. Okay, so to check the 4, we need to make sure the left and right side stay equal. You're not allowed to move things to either side of the equal sign. You just number crunch each side and make sure they come out to be equal. And so on the left-hand side, I get absolute value of 8, which is just 8. On the right-hand side, 1/2 of 4 is 2, plus 6 gives me 8. So that one works. And so 4 is definitely one of our solutions. Okay, and so to check the -12/5, we have to multiply it by 2 on the left, which is -24/5. You can think of it as 2/1. Multiply the numerator, multiply the denominator. And then on the right-hand side, 1 times -12 is -12, 2 times 5 is 10, and we're adding 6. Okay, back to the left-hand side, absolute value of a negative just becomes positive. So 24/5 is my simplified left-hand side. On the right-hand side, I need a common denominator. And so I am going to write 6 as 6/1, and we are going to multiply top and bottom by a 10 to get -12/10 plus 60/10, which we could have simplified the -12/10, but we're good. And so -12 plus 60 is 48. And then when I simplify this fraction, I can divide top and bottom by 2, which would give me the 24/5. And so this one does work. And so our solution set is -12/5 and 4. Neither are extraneous. Okay, last one on this page. First step is we need to isolate the bars, okay? Even though we can't combine this 3 with anything on the right-hand side, we still have to move it to the other side. And so I have absolute value of 1 minus 6n, and make sure your absolute values don't get mistaken for a 1, equals 4n minus 3. So my argument here is 1 minus 6n. We're going to write that twice, 1 minus 6n, no bars. And then we set it equal to the positive and negative right-hand side. So the positive would be just the 4n minus 3. And the negative would be negative 4n plus 3. The negative gets distributed. Every sign changes. Okay, back to solving a linear equation. First thing I'm going to do is subtract 1 from both sides. And then subtract 4n. And then divide by -10. Negative over negative cancels, and we can also divide both of those by 2 to get n equals 2/5. I'm going to wait to box it till we check it. Okay, over here, I'm going to subtract 1 from both sides. And then add 4n to both sides, giving me -2n equals 2. And it looks like we get an integer, -1. Okay, and so we go back to the original equation, and you don't have to go back to here. You can actually just go back to where you've isolated the bars. As long as you go to an equation that has bars in it, you are checking the right equation. So either this one or this one would work, just not these, not the cases. Okay, and so in one case we have 1 minus 6n in bars equals 4n minus 3. And I'm going to replace the n with a blank set of parentheses so we can fill in the value we are checking. Okay, and so when we check 2/5, remember, stay on the left and stay on the right. You're only allowed to number crunch. And so I get 1 minus 12/5, which is 5/5 minus 12/5, which is -7/5. And when we take the bars or take the absolute value, it's +7/5. Okay, on the right hand side, we get 8/5 minus 3, which is 8/5 minus 5/5, or 15/5, sorry, which is -7/5, and there's no absolute value here. And so now we end up with 7/5 and -7/5. Those are not equal. And so 2/5 is an extraneous solution. And you will need to be able to identify extraneous solutions. And so if you get an extraneous solution, you can just label it EXTSOL. You don't include it in your final solution set, but you do have to label it to get full credit. It's part of the Algebra 2 standard, is identifying extraneous solutions. All right, checking the -1. On the left side, we get 1, and then -6 times -1 is +6. So we get absolute value of 7, which is 7. On the right-hand side, I get a -4 minus 3, which is -7. And so once again, we're at a situation where I have 7 equals -7, which is not true. And so this is another extraneous solution. So both of the solutions we got were extraneous solutions. So EXTSOL. And so for our final answer, we would say no solution. And there's really no way to identify that from the very beginning because we have variables on both sides. All right, in this lesson, we are going to talk about how to write an absolute value equation for given situations. And so something that will help is that absolute value is used to measure distance. And so if you see absolute value of A minus B, that measures the distance between A and B. So for example, if you see X, absolute value of X, that measures distance from 0. And And so you can think of it as x minus 0 in the parentheses, which would simplify to x. And so we can measure the distance of any number from any number. So if I have x minus 3, that measures a distance of x from 3. And so that will help us write our equations. And so our first example says the Earth's distance from the sun in June varies no more than 0.23 million miles from 94.27 million miles. Write an absolute value equation that can be used to find the Earth's maximum and minimum distance from the sun in June. Okay, so we can kind of work backwards from this. And so the Earth's distance from the sun doesn't vary more than 0.23. So we could add 0.23 to the 94.7 or 27, or we could subtract. And so if I add, we can get that number exactly. 94, not that you need it, we're not actually trying to solve the problem. But that would be the maximum distance, is 94.5 million miles. Okay, if I wanted the minimum, I would subtract 0.23 from the 94.27. And we would get 94.04. And that would be the minimum. Okay, and so the goal of this problem is to write an absolute value equation that can be used to find these values. And so think about what we did. We started with 94.27 and we added and subtracted the 0.23 to get our max and minimum distance. Okay, and so we can think of that max and minimum distance, that value we want to know, as x. And then the plus or minus number is the distance. And so we want to measure the distance of some value from 94.27. And we know that it is positive or negative 0.23, or that distance is 0.23. And so when we measure the distance between some number and that 94.27, we want it to equal that value. And so here's our absolute value equation. And so the varying number goes here. I call it the varying number. The varying amount. And then I call this the from number. Okay, so from 94.27, and it varies no more than 0.23. And so let's look at another example. To work properly, the length of a machine part can vary no more than 0.05. That's my varying number, from 11.7 centimeters. That's my from number. Okay. Write an absolute value equation that can be used to find the maximum and minimum widths in centimeters for a machine part. Okay, and so you're always going to have x minus and then equals a number. It's minus the from number and equals the varying number. We want that distance to be on the right.